Imagine you are sitting at your computer, you write a piece of code, you create two identical things. Like, let's say you type out the exact same word twice and assign them to two different variables.
Right. A very standard thing to do.
Exactly. You hit run. Naturally, because you are a logical human being, you assume those two things exist in two entirely different places in your computer's memory. I mean, they are two separate lines of code. You type them twice.
Yeah, it makes total sense to think that.
But what if the programming language you trust is, secretly playing tricks on you behind the scenes?
It is the classic illusion of control. I mean, as developers, or really even just regular users of technology, we tend to think we are telling the machine exactly what to do.
Right, like we are the boss.
Exactly. We operate under the assumption that our instructions are absolute. But the reality is much more complex. The machine, or more specifically the language interpreter, is quietly editing those instructions. It's optimizing them, making memory decisions you are completely unaware of.
Which brings us to today's deep dive. We are looking at a fascinating article by Aaron Rose, and it's titled The Secret Life of Python Reusing Memory with Integer Caching and String Interning. And the setup for the source is actually a fictional vignette.
Yeah, it's a very creative approach.
It really is. The author places us in this grand Victorian library in London. So it sets this whole scene where craftsmanship and code quality are just the ultimate priorities.
The library serves as a brilliant narrative device, honestly. In this highly atmospheric setting, we are introduced to two software engineers. There's Margaret, who is the wise, seasoned senior developer.
And then there's Timothy.
Right, Timothy. He's her eager but somewhat naive junior colleague. And through their back and forth, we are guided through some very hidden, very consequential behaviors of the Python programming language.
Taking an abstract concept like memory management and grounding it in human conversation just makes the technical details incredibly accessible.
It really does. It takes the dryness out of it.
And that is exactly our mission for this deep dive. We are going to look under the hood of Python alongside Margaret and Timothy. We want to understand how Python manages memory, why it sometimes recycles objects right under your nose without asking permission.
Which is wild to think about.
It is wild. And we'll see how understanding a concept called object identity can actually save you from catastrophic bugs in your own code. Okay, let's unpack this.
Let us begin exactly where the source material begins, which is with a fundamental misunderstanding of how memory works. So Timothy wants to show Margaret that he understands the concept of an object.
Right, he's trying to impress the senior dev.
Exactly. He types out two lines of code, creating two distinct string objects. To his eyes, and to anyone reading the screen, they look identical. They contain the exact same characters.
He makes the completely logical assumption that they are living in two different locations on the heap. And for anyone listening who might be a bit newer to how memory is structured, the heap is essentially just the general pool of memory in your computer.
That's a good way to put it.
You can think of it like a massive, sprawling warehouse where the program goes to find empty shelves to store dynamic data while it runs. So Timothy assumes that because he typed the string twice, he is renting out two separate shelves in that warehouse.
He is very proud of this deduction, too.
Oh, yeah, he fully expects a pat on the back from Margaret.
But Margaret stops him in his tracks. She challenges his basic assumption by asking if he thinks Python treats memory the way a human treats a printing press.
A printing press?
Yeah, because a printing press stamps out a new physical copy every single time the crank is turned. If you print the same page twice, you have two physical pieces of paper taking up, physical space in the room.
But Python doesn't work like a printing press. Margaret delivers this great line in the text. She says, Python is lazy and memory is expensive. I love the phrasing there, like calling a programming language lazy.
It's funny, but that laziness is actually a deliberate, highly engineered design choice. I mean, memory space in a computer is a finite resource. When a program runs, it needs to constantly allocate and deallocate chunks of memory for the data it is processing. Finding an empty shelf in that warehouse you mentioned, placing the data there, and then clearing it out later, that all takes CPU cycles.
It's a lot of work for the computer.
Exactly. If you are constantly carving out new blocks of memory for identical pieces of data, you are wasting precious resources. You're slowing down the entire operation.
So to prove her point, Margaret has Timothy open up his interactive shell to look at the fingerprints of these two strings he just created.
And he is in for a surprise.
Total shock. When he inspects them, he sees that the two identical long strings of integers that pop up on his screen are the exact same number. Even though he typed the literal string out on his keyboard twice, the computer is telling him there's only one thing there.
This is the big moment of revelation. Margaret explains what the CPython interpreter, which is the standard, most widely used implementation of Python, is actually doing behind the scenes. When the interpreter reads Timothy's code, it recognizes that the string literal he typed is immutable. And immutable simply means it cannot be changed once it is created.
Because a string is just text. You aren't going to suddenly change the first letter of that specific text object in memory. If you needed a different word, you would just, create a totally new string.
Precisely. And because the interpreter knows this string will never change, it decides not to waste effort. Instead of carving out two separate shelves in the warehouse for the two variables, it creates the object once.
Just one time.
Just one time. It then points both of Timothy's variables to that exact same memory address. In technical terms, it interns the string.
Okay, let me make sure I'm visualizing this perfectly for the listener, and I want to use an analogy drawn from Margaret's chalkboard lesson in the source text.
For it.
So instead of variables being separate physical boxes that contain their own data, they are actually just different name tags pinned to the exact same individual.
What's fascinating here is that Python does this entirely automatically at compile time.
Really? You don't have to tell it to do that?
Nope. If you create strings that look like valid identifiers, meaning they only contain letters, numbers, or underscores, the interpreter silently intervenes. It pins those different name tags to the single individual, exactly as your analogy describes, to optimize performance and save space.
Wow.
It's a brilliant optimization, but as Timothy is learning, if you do not know it is happening, your mental model of your code is fundamentally flawed.
It completely flips your understanding of what a variable even is. I mean, a lot of us are taught early on that variables are containers. You put a value in the container.
That's the standard beginner lesson, yeah.
But Python variables aren't containers at all. They are just pointers. They are just arrows directing traffic to a specific location in memory.
This revelation sets the stage for the next logical exploration in the library. If Python recycles strings to save memory, what else is it recycling? How deep does this laziness go?
Right, because if Python is secretly recycling text to save memory, it must be doing the exact same thing for numbers. I mean, math operations are constant in programming, so saving memory on numbers would be a huge performance boost.
Absolutely.
But before we get to how numbers behave, we need to understand how Margaret proved this to Timothy in the first place. She mentioned looking at the fingerprints of the objects. How do you actually look at the physical memory address in Python?
The source introduces us to what we might call the ultimate truth teller in Python. It is a built-in function called id.
Id. Margaret's cheat sheet in the text highlights this specifically. The id function strips away all the magic.
It really does. The
Yeah.
id function returns the actual memory address of an object in the standard CPython implementation. It forms the absolute bedrock of object identity.
Because values can lie to you, right?
Exactly. In programming, values can easily lie to you. Two things can look exactly the same, like two separate pieces of paper with the same text printed on them, but be entirely different entities.
Yeah.
But the id function cannot lie. It gives you the exact unique numerical address where that specific object lives on the heap.
So when Timothy ran id on his first variable and then ran id on his second variable, the terminal spit out the exact same long string of numbers. That's how he knew they were the exact same object. The truth teller proved it.
And Margaret uses this truth teller to demonstrate something even more surprising about integers. She sets up a side-by-side comparison for Timothy to test out his new understanding.
She has him assign the number 256 to a variable and then assign 256 to another variable. They run the id, check, and it returns true. The IDs are the same. Python is recycling the number 256 just like it recycled the string.
Correct.
Here's where it gets really interesting, because if variables assigned the number 256 share an id, then surely 257 does too, right? I mean, they are just numbers on a number line.
You are stepping into the exact trap Margaret laid for Timothy.
Am I?
Yes. Timothy has the exact same reaction. He says, wait, why does 256 return true, but 257 returns false? They're just numbers.
Well, yeah, to human logic, there is no meaningful difference between the integer 256 and the integer 257. They are literal next-door neighbors.
Right, but why would Python treat them differently? If the interpreter is lazy, shouldn't it be lazy all the time?
That's what I'm asking.
Margaret introduces this mind-bending reality called integer caching. To the interpreter, these are not just numbers. CPython has a very specific, hard-coded optimization built into its architecture. The moment CPython boots up, like before you even write a single line of code, it pre-allocates a global array for small integers.
Small integers.
Specifically, integers from -5 up to 256.
Wait, hold on. The moment I open Python, those specific numbers are already sitting there in memory, fully constructed, just waiting for me to use them.
They are completely pre-created. When you ask Python for the number 10 or 100 or 256, you are not creating a new object. The interpreter just hands you a recycled object from that pre-allocated cache.
That is wild.
It is. Because those small numbers are used so frequently in loops, counting, and basic logic, it saves a tremendous amount of time to just reuse them. So the id for 256 will always match, because every variable is pulling from that same cached object.
But 257 lies outside that safety boundary.
Exactly. For 257, Python is forced to carve out entirely new memory blocks. Because it is not in the cache, every single time you assign 257 to a variable, Python treats it like a brand new request.
So it goes out to the warehouse, finds an empty shelf, writes 257 there, and points the variable to it.
You've got it. So if you assign 257 to variable A and 257 to variable B, they will have totally different addresses.
Even though the mathematical value is exactly the same.
Yes, they are two completely distinct objects in memory. You cross that arbitrary boundary line, and everything changes. Inside the boundary, everything is recycled and shares an identity. Outside the boundary, everything is uniquely created.
It completely reorients how you have to think about the code you are writing. It's like finding out that every time you ask for a coffee under $5, the barista just pours you a cup from a massive communal pot sitting on the counter.
Right, the cheap coffee is pre-made.
But the second you ask for a coffee that costs $5.01, they pull out the grinder, get fresh beans, and brew you a brand new individual cup from scratch.
The barista analogy perfectly captures the sudden shift in behavior. Margaret draws a line on her small slate board to illustrate this exact boundary. She emphasizes again that you are looking at different name tags.
Right.
In Python, variables do not hold values. They are merely references pointing to objects. Until you understand the id function, you do not truly know who you are talking to in memory.
This secret memory recycling is undeniably fascinating. I mean, I love peeking behind the curtain of the interpreter to see how the sausage is made, but I have to play devil's advocate here for a second.
Okay, let's hear it.
So what does this all mean? If variable A equals 256 and variable B equals 256, why should you, sitting at your keyboard right now, actually care if they share a memory address?
It's a fair question.
They are both 256. If you add them together, you still get 512. But why does understanding integer caching matter in the real world?
That is the crucial question, and it's the entire reason Margaret is giving this lesson. Understanding this theoretical knowledge is vital, because failing to understand it leads directly to a very specific danger zone.
Oh boy.
Yeah. It leads to the is versus other trap.
The trap. Okay, let's dig into the cheat sheet from the source material, because Margaret breaks down the critical difference between these two operators, which, they look very similar to a beginner.
They do. In Python, you have two different ways to compare things. You have the double equal sign, which is equals, and you have the keyword is. They might seem interchangeable at first glance, but they are asking two fundamentally different questions of the interpreter.
Okay, what's the first one?
The operator checks for equality. It asks, do these two objects contain the same data? Do their mathematical or textual values match?
So if I have two different physical apples, and I ask, are they both apples? The operator says true.
Exactly. But the is operator checks for identity. It asks, are these two variables pointing to the exact same id address? Are they literally the exact same object occupying the exact same shelf in the memory warehouse?
Oh, I see. So going back to my apples, if I hold up an apple in my left hand and an apple in my right hand, and I use the is operator to compare them, it would say false.
Right.
Even though they're both apples and they have the same value, they are not the same physical apple.
This distinction is where the stakes get incredibly high. Margaret's cheat sheet provides a stark warning. Blindly using is instead of for value comparison introduces silent catastrophic production bugs.
Let's paint the picture of this catastrophe, because the source spells out a terrifying scenario for a developer.
It's every developer's nightmare.
Imagine you are writing a script, maybe a financial application or a data processor. For some reason, you use the is operator to check if a variable equals a certain number.
And when developers write tests on their local machines, they often use small, simple numbers. Say they test their logic using the number 100 or the number 250.
Wait, I see exactly where this goes wrong.
Do you?
Yes. If a developer uses 100 in their local testing, those tests are going to pass perfectly. The integer cache is handing out that shared communal object for 100, so the id matches.
Exactly.
The is operator returns true, just as the developer expected, even though they used the entirely wrong operator for checking a value. They're going to get a false sense of security.
The environment itself hides the flaw. The code works flawlessly on their machine.
They will think their logic is bulletproof. They commit the code, deploy it to production, and go to sleep. Then, real-world data hits the application. A user inputs a massive number, something like 50,000.
Uh-oh.
The application takes that number, compares it using the is operator, and it fails spectacularly.
Because 50,000 crosses that caching threshold of 256. Python carved out entirely new memory blocks for those numbers. They have the exact same value, so would have worked perfectly.
But because they have different memory addresses, the official operator suddenly returns false.
And your application crashes. Or perhaps even worse, it quietly corrupts data without throwing an explicit error because the logic branch just failed silently.
It is such a devious bug because it is environmentally dependent. The logic is flawed from the very first keystroke, but the Python interpreter's secret cache acts like a smokescreen until it's too late.
Margaret stresses that understanding it and the caching rules is non-negotiable for writing robust code. If you do not know the boundary exists, you cannot protect yourself against crossing it.
It really puts the responsibility back on the programmer to know their tools. I mean, Python gives you speed, but it demands you understand how it achieves that speed.
If we connect this to the bigger picture, this behavior highlights the delicate balance language designers have to strike between developer convenience and machine performance. Python does this automatically for small integers and certain strings to make the language fast and efficient out of the box.
Right.
But the source also mentions that developers are not entirely locked out of this optimization process. You can actually take control of it.
The cheat sheet mentions manual optimization, because while strings that look like basic identifiers are automatically interned at compile time, we have to consider dynamic strings.
Right, strings that change.
I'm talking about strings generated at runtime, perhaps from a massive database query or unpredictable user input.
Python won't automatically intern those dynamic strings.
But why wouldn't it? If saving memory is the ultimate goal, shouldn't the interpreter recycle everything it possibly can, regardless of where it comes from?
You would think so, but evaluating every single new string at runtime to see if a copy already exists actually costs more performance than it saves.
Ah, I see. The interpreter would have to scan the entire memory warehouse every single time a new word pops up, just to check if that specific text is already sitting on a shelf somewhere. That scanning takes time.
You would introduce a massive bottleneck. The interpreter would be spending all its CPU cycles just comparing text instead of executing your logic.
Yeah, it makes total sense.
However, if a developer knows they will be comparing a specific dynamic string heavily, say, checking thousands of records against one specific database value, they can manually optimize performance using a built-in module. They can use a command called sys.intern.
Oh, so you can explicitly tell Python, hey, I know you usually wouldn't recycle this string because checking takes too long, but I'm going to be using it constantly, so please take the time to intern it and save me the memory.
Exactly. By calling sys.intern, you force the interpreter to check its internal dictionary of intern strings. If the string is there, it points your variable to the existing object.
And if it's not?
If it is not, it adds it to the dictionary. It allows you to leverage the interpreter's optimization mechanisms on your own terms.
That's incredibly powerful.
But you can only do that if you understand that interning exists in the first place. You have to understand the mechanics before you can master them.
This has been an incredible journey. I mean, we started in a quiet Victorian library with a junior developer who thought he knew how memory worked, and we ended up unraveling the secret, hard-coded optimizations of the CPython interpreter.
Moving from seeing variables as physical boxes holding values to understanding them as name tags pointing to fluid memory addresses is a profound shift in perspective.
It really is. Let's do a quick recap of the major takeaways for everyone listening.
Sounds good.
First, remember that variables are just name tags or pointers, not containers. Second, the id function is the ultimate truth teller. It strips away the illusion of value and shows you the actual physical memory address.
And third, CPython secretly recycles small integers from -5 to 256 and interns certain strings to save memory space and CPU cycle.
The most critical practical application to take away from all this, confusing identity, the is operator with equality, the is operator, is a recipe for disaster.
Please, never use is when you mean to check. if two values are mathematically or textually equal, because Python's hidden caching will eventually betray you in production.
That is exactly why this deep dive matters for you. Knowing how to write code is one thing. Knowing why a language behaves the way it does and understanding the hidden logic of the interpreter is what elevates your
It
skills.
really separates the novices from the experts.
It takes you from just blindly typing instructions to truly mastering the craft, just like they strive for in Margaret and Timothy's library.
Anticipating problems based on the architecture of the language is always better than just reacting to mysterious bugs in a live environment.
You stop being at the mercy of the machine and you start working in true partnership with it. Before we wrap up, we want to leave you with one final thought to mull over on your own. We've spent this entire time unpacking how Python quietly manages memory and bends the rules just for numbers up to 256 in small strings.
Right?
So ask yourself, if CPython is doing all this secret recycling and routing under the hood just for those specific things, what other assumptions about your code are actually just illusions created by an interpreter trying to save a few bytes of memory?